Welcome, everybody. It's my pleasure today to introduce Teresa Heiss, who's actually one of our new AATRN co-directors, and she'll be telling us about geometry and topology of periodic point sets, for example, crystals.
Thanks, Henry, for the nice introduction. Yeah, my name is Teresa, and the reason I want to talk about geometry and topology for periodic point sets is that crystals can be modeled as periodic point sets. This is joint work with my supervisor, Herbert Edelsbrunner, and also with Alexey Garber, Vitaliy Kurlin, Georg Osang, Janos Pach, Morteza Saghafian, Philip Smith, and Mathijs Wintraecken. And before I start, I want to say that I really like talks to be interactive, so feel free to just interrupt me if something is unclear. The talk will consist of two parts, where the first one is about an application in material science that has interesting aspects of computational geometry and computational topology inside. Namely, it's in crystallography, and it's about finding fingerprints that somehow characterize crystals uniquely and continuously. And I will explain what I mean by that. And then I will give you two examples, or at least candidates for fingerprints, namely the density fingerprint and the persistence fingerprint. And you will see that this topic will lead naturally to the second part of the talk, namely how to define persistence for periodic sets. So I will tell you some definitions that might seem like a good choice, but that do not work. And this shows how much more difficult this problem is than one might think at first glance. And then I will give you a definition that actually works. But this definition also has some shortcomings. And so I will talk about the shortcomings and about how we will maybe be able in the future to fix those shortcomings to get an even better definition. Okay, so we want to find fingerprints for crystals. What is a crystal even? I need to define that. So a crystal is not just those fancy, shiny gems that you might think of. I mean, those are also crystals, but it's more than that. Namely, for example, in pharmaceuticals, in those little capsules, there are also many little crystals. And this kind of makes it clear that studying crystals is something useful. A crystal is a solid composed of atoms, ions, or molecules arranged in a pattern that is periodic in 3 dimensions. So that means there exist 3 linearly independent directions. The third one you have to imagine coming out of the screen, such that each of these translations maps the crystal to itself. It's invariant under those translations. You will see that like this graphic, also all my other graphics are usually in 2D, but the whole talk will be about 3D crystals. So just always imagine everything that I show you in 2D in your head in 3D. For those of you who know what a quasi-periodic crystal is, in this talk, I will not talk about quasi-periodic crystals. So every time I say crystal, I actually mean periodic crystal. So the thing that I just defined before. We model a crystal by modeling each center of every atom as a point, and then we get a periodic point set. This is simply a set that is invariant under 3 linearly independent translations. But such a periodic point set consists of infinitely many points. You need to imagine this extended in all directions. And that means that we would want to work with some kind of finite representation instead. And the finite representation is simply a little tile that you cut out of your crystal, such that copying this tile infinitely often in all directions gives you back the periodic point set. So such a finite representation is simply a unit cell, which is a parallelogram that is spanned by vectors in 2D only by 2 vectors, v1, v2. In 3D, there is a third vector, v3. And then inside this unit cell, there is a finite point set that we call the motif. And then we describe our representation simply by the vector spanning the unit cell and the motif inside the unit cell. But there's a problem with these representations, namely they are not unique. So you can see here that A, B, C, and D are different tiles cut out of the same crystal. So all these representations represent the same crystal. And because of this, we want to define now what it means that representations define the same crystal, that they are equivalent. They're equivalent if you take your one representation, you copy it infinitely often in all directions, you take your other representation, copy it infinitely often in all directions. And if there is an isometry of Rn, or because we said everything is an R3, an isometry of R3 that maps one crystal to the other crystal, then we call those two representations equivalent. Because if you take a crystal and you just rotate it or translate it or even mirror it, it makes sense to still call it the same crystal. Okay, so mirroring, that's not so obvious that this should be allowed, that it can be up for discussion, but in this whole talk, I will allow mirroring as well. So all isometries are free. Okay, so if that's the case, then these two representations are called equivalent. But we don't only want to know when two representations give exactly the same crystals. We also want to know when two representations give similar crystals. So crystals that might just be that you have to perturb every atom a bit and you get to the other crystal. So we want to compute the distance between them, or define the distance between them firstly. Okay, so the distance is defined by first taking, again, the one unit cell, copying it infinitely often in all directions. That gives a point set P. The other unit cell gives a point set P prime. And then we look again at isometries of R3. But this time, the isometry doesn't need to map the point set exactly to the other point set. It just needs to map it close enough to the other point set. So then, after applying this isometry, we compute the bottleneck distance, which is simply the you take the best matching between those two point sets, and then you check how much the points have to move at most in this best matching. So the length of the maximum length of those red arrows that I've drawn here. Okay. But if we want to compute this distance in practice, we don't want to define it as an infimum. We want something more possible to compute. And so what crystallographers nowadays do is that they try to find the representant of the first crystal that looks most similar to the representant of the second crystal. And then they compare only those two similar looking crystal representations. But that's a difficult task. So that's a current problem in crystallography, how to find the most similar looking representation. So what we do is to completely avoid this problem and to just take a different approach. Namely, instead of computing the distance between the crystal representations directly, we just map them to a different space, to a fingerprint space. And then we compute the distance between the fingerprints instead of the distance between the crystals. So we map our representation of a crystal, or better, the whole equivalence class of representations of a crystal, to a so-called fingerprint in some nice metric space. And for this to make sense, we need 4 properties. Namely, the first one is invariance, which is simply well definition of this function. Namely, we want that if two representations represent the same crystal, so if they're equivalent, then they should get mapped to the same fingerprint. The second is continuity, and it's actually similar to the first, because now we want to say that if two representations are very similar to each other, they should get mapped to fingerprints that are also very similar to each other. And the third one, injectivity, is the opposite of the first one. Namely, if two representations represent different crystals, so they're not equivalent, then they should get different fingerprints assigned. And if you think about it, that's a pretty strong property, namely that if you think of hash functions, for example, for hashing files, then it's okay if there are some collisions, like some files that get the same hash assigned. You only ask for it to be not too likely that this happens. But here, the way it's formulated, we would really ask for no collision at all. And then the fourth condition is the maybe most vague one, namely that it should just be possible to compute it efficiently. And by efficiently, I mean that it should be possible to implement this algorithm in practice and yeah, to be useful in practice, not taking too long to compute, whatever this means. And like I said, we completely avoid this difficult problem of finding the most suitable candidate for computing distances. Namely, we just take any representant, we map it to its fingerprints, and it doesn't matter which representant you give me, because all the different representants of the same crystal will anyway give me the same fingerprint function. And then I compute the distance between the fingerprints, and this distance doesn't need to be exactly the same distance as the one between the crystals, but at least it's easier to compute. And we know that if the two crystals are very close to each other, then those two fingerprints will also be very close to each other. So why do we even want the fingerprint function? Like I already said, we can compare crystals by comparing their fingerprints. And this is, for example, important in the application crystal structure prediction, because there, these material scientists simulate many, like thousands of crystals, where many of them are extremely similar to each other. So they simulate them on the computer, and the computer doesn't know that it produced some instances that are extremely similar to each other. And so it would be good to find out which of these thousands of crystals are similar to each other and which not. And this could maybe even then save some computation time if you don't need to do something twice for two crystals that are anyway extremely similar. And in general, if we map our crystal space to some easier space, then maybe this helps us to develop some better understanding for the space of crystals. So this could be useful in many ways. And if your fingerprint has a vector representation, then it could be used to do machine learning on the fingerprints instead of machine learning directly on the crystals themselves. Okay, so let's find such fingerprint maps with these properties that we talked about before. The first one is the density fingerprint, and it's constructed in the following way. So given is this point set, periodic point set, which you see marked by black points in this picture. And then you take balls around your points and you increase the radius of these balls. And when you increase the radius, they start overlapping, and you color the different regions differently. Namely, everything that is covered by none of the balls is in this teal color. Everything that is covered by exactly one of the balls is in dark blue. Everything that is covered by exactly two of the balls is in green, and so on. 3 balls is orange, and so on. And then we want to compute the fractional volumes of those different colors. So you can compute those fractional volumes within one unit cell. And the density fingerprint is then simply a bunch of functions, namely actually infinitely many functions. We've drawn here only the first 8 density functions. But of course, if you let the radius increase arbitrarily high, then there will also be arbitrarily high k-fold intersections. Okay, so the density fingerprint is a bunch of functions, namely for each color one function. And this function tells you how the fractional volume of that color increases when the radius increases. So the density fingerprint tells you at a certain radius, for example, 0.55, how much proportion of the space is covered by no ball at all in teal, how much is covered by exactly 2 balls in green, and how much is covered by exactly 1 ball in blue. Okay. And now we need to make sure that the density fingerprint fulfills those properties that we would want it to fulfill. So firstly, the invariance, or maybe I should say first, I won't have time to go in all of them in detail, but I will look at one of them in more detail, namely the computability. So for this, I will give a proof sketch. But yeah, let's start with invariance. Just quickly, that just means that if you choose a different unit cell and compute the fractional volumes within this unit cell, this shouldn't change anything, which seems very plausible. Then continuity, we even prove something something stronger, namely Lipschitz continuity, where the Lipschitz constant depends on two parameters of the periodic point set, namely packing and covering radius. But if you want to know more about this, then you can just read it up in our paper about the density fingerprint. Then the third item is efficient computability. So there are now two ways I could convince you that what we do is efficient. Namely, firstly, by telling you that we actually implemented this software and we ran the software over more than 5,000 crystals to compute the density fingerprints. And so the first 8 density functions, of course, we had to stop somewhere. And we did this in 10 hours on a laptop. So 10 hours might sound a lot, but in this application, crystal structure prediction, they often use months of supercomputing time. And so 10 hours on a laptop is, compared to that, not much. And if it even helps then reducing this supercomputing time, then this is totally worth it. Okay, if you're more theoretically inclined, then maybe you will be more convinced by seeing the theoretical bounds of our algorithm. So let's also go through that. We compute the density fingerprint using Brillouin zones. So we'll now explain what Brillouin zones are. The cave Brillouin zone of a point A in a point set capital A is the set of points that has A as its exactly cave closest point. So for example, if you look at this pink region that has a 6 inside here, then every point in this region belongs to the sixth Brillouin zone, because the point A is the 6th closest point. There's this point that is even closer, the 2nd and the 3rd and the 4th and the 5th. They are closer, so A is the 6th closest point. Okay. And using those Brillouin zones, we can prove this theorem about how to compute the density functions. Actually, this is a theorem about how to compute the fractional volume covered by at least k balls. If you remember, before I defined the density functions as covered by exactly k balls, but that's really a small difference. Once you have one, you can get the other. Like the fractional volume covered by exactly k balls is just covered by at least k balls minus covered by at least k plus 1 balls. Okay, and you don't need to look at the formula too precisely, because we will just derive it together with a little proof sketch. So if you have a periodic point set A and balls of radius t around every point, and we want for every point to know whether it is covered by at least 3 balls. So in this case it is. And how could I have found this out? I could have just looked which of my points of A is the exactly 3rd closest point. So in this case, it's the point A. And then I only need to check whether the black point lies in the red circle, not whether it lies in any circle, because if it's in the circle of the 3rd closest ball, then it's even more in the even smaller, even closer balls. Okay, so we only need to check whether it's in the ball of the exactly 3rd closest point. And this already reminds us of the Brillouin zone. So let's overlay this with the Brillouin zone. And so you see this, this black point that I chose is in the 3rd Brillouin zone of A. And therefore, to see whether it is within covered by at least 3 balls, I just need to check whether it's covered by the ball around A. And so then there's something else that is nice about Brillouin zones that we need here, namely that every point has some 3rd closest point. And this means that the 3rd Brillouin zones of all the different points, they tile space. And so we can compute the fractional volume only within the 3rd Brillouin zone. And it's easy, we just intersect the 3rd Brillouin zone with a ball. And this is what the formula tells us. We take the cave-Bruyère zone, we intersect it with a ball only around the point A, we compute the volume of that. We do that for all different points in the motif. And then we normalize by the volume of the unit cell. Okay, so now that we have a way how to compute the density functions, we can think about how the complexity of the algorithm can be. And again, for details, you need to check out our paper, but we proved there that evaluating the first k density functions for one given radius t takes time that is linear in the number of points in the motif and cubic in the number of density functions that we want to compute. Okay, so much about computation. The last point is injectivity. And we proved injectivity generically. So in the paper, we give some genericity conditions. We tried to come up with a counterexample against injectivity, and we didn't find any. So it's still open whether it is really injective or only generically injective. And we really tried hard. Like we came up with good candidates, but none of them worked.
So Teresa, now's probably a good time for a question. There's a question from Mikael Vejdamo Johansson in the chat. He didn't quite catch the formula. Does the complexity vary with ambient space dimension, i.e., is the complexity different between working in the plane and 3D space?
So we did everything in 3D because it's not very different in other dimensions. It's just that the constants change a bit. So I would have to think now about how it changes. Yeah, I would guess that the 3 would probably be a 4 in higher dimensions, but I would have to think it's a D in D-dimensional space. But I would have to think it through. But yeah, it should be easy. Like if you would look at the proof in our paper and just doing the same things for D dimensions instead of 3 dimensions, it should be easy to derive the bound. He asked more things.
There's a different question from Sanki. So could you say more about the vector representation? I don't know if you have more to say.
Yeah, so you will see actually that the next fingerprint, not this one, but the other one, the persistence fingerprint, computes persistence diagrams, and persistence diagrams have different vector representations, for example, persistence landscapes or persistence images. And so this would mean that we can then represent our crystal by a fingerprint, and we can represent the fingerprint by a vector. And once it's a vector, we can, for example, apply artificial neural networks more easily than for the crystal itself, which is somehow a bit more weird, because you can, of course, describe it as a vector, namely the free vector spanning the unit cell plus the coordinates of the points in the motif. But then if you slightly change those vectors, or if you change those a lot, then it might be that you actually end up again with the same crystal. So this non-uniqueness makes the space of crystals very not nice, and this would hopefully then be nicer. Okay. So should I then continue, Henry, or is there more questions?
No, yeah, please go on.
Okay. So the persistence fingerprint is the second fingerprint I want to introduce. So about that one, we didn't publish a paper yet because this is still more ongoing work, and you will see why in the end. So we again do the same thing. We look at these growing balls, but now instead of looking at how the volume of those different colorful regions changes, we look instead at how the homology of those different colorful region changes. And the reason for that is that the density fingerprint seems somehow like a waste. Like we give a function value for every radius of balls, and there are infinitely many possible choices for radius of balls. And the really interesting thing happens only at this, like at discrete values, namely The density functions are analytic functions, piecewise analytic functions. And those places where it's analytic before and analytic afterwards, but not in that point, those are the interesting places, because this means that if you grow balls and if they don't touch, then everything, the volume just changes analytically. But then when they start touching, there is a sudden kink happening. And yeah, and those balls touching, those are the where the combinatorics of the balls really changes, where the topology changes. And so it kind of makes already sense that these places where the density fingerprint will have a kink will be those places where the persistence diagram will have a birth or a death value. But first, I should explain what a persistence diagram even is. So it measures the shape of a point set. I'll do this quickly because many of you already know what a persistence diagram is. I just take balls around my points and I increase the radius. And sometimes new features are born. So for example, here we have a hole and this hole persists. And at some point it dies. And we remember those birth-death pairs. And in the next step, for example, here, there is another hole born and it persists and it dies. And we put those birth-death pairs in a so-called persistence diagram, where every point in the persistence diagram is the birth radius of a homological feature and the death radius of a homological feature. Birth is x-coordinate, death is y-coordinate. Okay, and usually we compute persistence of the union of balls, but we can also do it of the k-fold cover. So the k-fold cover is simply the regions that are covered by at least k points. This is a two-fold cover. Three-fold cover is just the union of triple intersections, and so on. And if I now fix k, for example, k equals 2, and I look at how the two-fold cover increases when the radius increases, then I get a nested sequence. So I've plotted this nested sequence for k equals 2. So I only plot the two-fold cover, not the balls themselves. And the two-fold cover grows and new connected components are born. And then those connected components, some of them die. And a new one-dimensional hole is, for example, born. And this also dies. And so this, we can compute persistent homology of that nested sequence. And we call it order k persistence. And I can do this for every possible choice of k, infinitely many choices. And this sequence of persistence diagrams I then call the persistence fingerprint. And I see there's a question. Homology of k-fold covers. Yeah. Yeah, so that when I describe it here, it looks as if I would really look at those growing balls, but of course, that's not a good way to discretize this in the computer. So what we do instead is we compute persistence of the order k Delaunay mosaic. So the usual persistence you can discretize with the normal Delaunay mosaic, and order k persistence you can discretize with order k Delaunay. And yes, there is software for that. Okay, yeah, but so I defined this persistence fingerprint, but bear in mind, I only defined this for finite point sets X. So if we want to use this as a definition for the persistence fingerprint, the input is an infinite periodic point set S. And so this means that we need a new definition of what persistent homology or k-fold persistent homology means if we have an infinite periodic set as an input. And this leads to the second part where we define persistence. So now we'll not specifically focus on this order k persistence, but just persistence in general for periodic sets or periodic functions. So first, what does not work? The most easiest thing would be to just define the persistence diagram as the persistence diagram of the point set. The singular homology is also defined for unbounded topological spaces with infinitely many holes. So this just means that every homology group will be infinitely large, but you can still look at the sequence of homology groups and you can still define persistent homology. But the problem is that each multiplicity you would then get in your persistence diagram. So each pair in the persistence diagram would appear infinitely often. Because if a hole appears somewhere, it also appears in all its periodic copies. And those are infinitely many, so it will appear infinitely often. Okay, so let's try to come up with something. Yeah, and maybe I should say, like, what's the problem with each multiplicity being infinity? This completely removes the information about multiplicity, because if something appears exactly twice as often as something else, then 2 times infinity is still infinity, and so you don't get this information. So yeah, that's not what we want. Also, it would probably take infinitely long to compute. That's also not good. Okay, but let's come up with something different, something that only takes finitely long to compute. Let's take a unit cell and let's identify the opposite boundaries with each other. And we call this then computing persistence with periodic boundary conditions. So we compute persistence now of this finite tile, this finite representative of our periodic point set with periodic boundary conditions. That seems nice, but the problem is that it's not invariant under choice of unit cell. So here I have 2 different choices of exactly the same, like 2 different choices of unit cell for exactly the same periodic point set. And I can compute persistence of both of them. On the left, I get this circle that creates a homology class, namely one homology class, and the horizontal cycle is also a cycle because we have periodic boundary conditions. And this also appears once. But on the right-hand side, the circle appears 2 times and the circle appears 4 times and the horizontal cycle appears 2 times, sorry. They appear a different amount of times, that's the point. And so taking it like this doesn't work. Okay, you could say now we can somehow normalize it, but we would have to normalize it somehow differently for different cycles, because the circle increases with a factor 4, whereas the horizontal cycle only increases with a factor 2. So that seems like a hurdle that we might still manage to overcome, because we could look at how often does a cycle cross the boundary of the unit cell. And then we would see a difference between those 2 cycles, and we could use this to normalize them also differently. So it might be possible. But then there is a different problem. Namely, let's look at this example. So this looks a bit like DNA. So 2 strings that are twisting around each other. And so one string starts at the bottom and ends at the top, which is exactly where the other string starts. And this one ends at the bottom, exactly where the first one started. So if you compute persistence with periodic boundary conditions for the first choice of unit cell, then you will get 1 cycle from this, because it's all connected. And if you compute persistence with the second choice of unit cell, you will get 2 cycles, because now they're not connected anymore. And then if you go to 3 cycles again, they become connected again. So you only get 1 cycle. This is a very, very weird behavior. In particular, if you look at the second choice of unit cell, then you get those 2 cycles, and you would get exactly the same persistence diagram if it was just 2 parallel cycles. But somehow they behave very differently, in the sense that scaling it, choosing a different choice of unit cell, like the scaling behavior is very different if it's 2 intertwined or 2 just parallel cycles. So it would not at all be clear how to normalize it. Not like, how would we even want to normalize this? This is completely unclear. So this counterexample made me and my collaborators think that, okay, maybe this is just not the best direction, and let's try something completely different. And whoops, skipped something. Yeah. So now now comes the definition that finally works. Namely, you take larger and larger windows, these windows uj that are just j times j times j copies of your unit cell, and you compute persistence of those finite point sets inside the window, and you normalize it by the window volume, and you take the limit. So let's look at this in detail. These are the windows uj for j equals 1, 2, 3. We look at those as just finite sets. We compute persistence of each 3 of those finite sets. We divide by the volume of the window size. And then we take the limit as j goes to infinity. Okay, but computing this limit sounds difficult. It sounds like you would have to compute infinitely many different values of j. But it's actually easier, because we are currently in the process of writing down a proof that for large enough j, these multiplicities will scale polynomially. And so we can fit a polynomial through the multiplicities of each of the persistence pairs. And then for each persistence pair, we take the, in 2D, quadratic coefficient. In 3D, it would be the cubic coefficient. And we normalize that one by the volume of the unit cell. And this gives us exactly the same persistence diagram than in the process we did before. Because taking a polynomial and dividing it by j squared times the volume of the unit cell and taking the limit is the same as just taking the quadratic coefficient and dividing it by the volume of the unit cell. Okay. Yeah, note something interesting, namely that those are non-integer multiplicities, which I find funny because I haven't seen this in applications or in other applications. And here it really makes sense because we divide by the volume of the unit cell in order to make it independent under choice of unit cell. And so you can imagine this number of 3.6 means that there appear 3.6 features per square meter, so per unit volume. And yeah, and so I think it's cool that those non-integer multiplicities appear, and they actually don't harm. You can also compute the bottleneck distance or something like this if you have non-integer multiplicities. I see there's another question.
Yeah, I'll ask this at the end of the talk, Teresa.
Okay, yeah. Perfect. Okay, so that was our definition that finally works. So we can use this definition for defining the persistence fingerprint. So now we have the new definition of k-fold persistence, because everything that I explained was for persistence, but it works the same for k-fold persistence. Sorry, order k persistence, like 2 names for the same thing. And I would still like to continue, although we already found the definition that works, because this definition has a problem. Namely, it doesn't capture cycles that do not appear a cubic number of times. So this cycle, for example, it's just you have a 3-dimensional unit cell with a tunnel that goes from bottom to top. And if I take 2 times 2 times 2 copies of this unit cell, I only get 2 times 2 copies of that tunnel. And so that means it doesn't scale. The polynomial with which it scales, if I increase my window size uj, is not cubic, but it's instead a quadratic polynomial. And in 3D, our fingerprint, our definition captures only the cubic cycles. So yeah, we have some ideas how to define it in a way that would also capture those non-cubic cycles, but that is work in progress. Okay, so let's conclude. We talked about finding fingerprints for crystals. We had those two different candidates, one that focuses more on the volume and one that focuses more on the homology. And the future work is that first, of course, we have to prove that our new definition really has the desired properties that one would want from a definition. Then with this, we can, as I said, plug it into our definition of the persistence fingerprint. And then it should be possible to just prove the same properties that we have already proven for the density fingerprint, also for the persistence fingerprint, because as I already mentioned before, those two, they are very related. And so some of the proofs might be or seem to be completely just taking the same proof idea now for the persistence fingerprint instead of the density fingerprint. And then, as I also already mentioned, we would be interested in extending the definition to also capture those non-cubic cycles. So those 3 points seem relatively close future work. And then in the maybe further future, we could try to, or we already did try, but we didn't manage so far, proving injectivity without genericity conditions. That seems pretty hard. Then something that should be straightforward is just generalizing this to weighted points, because now we just talked about points where every atom is just modeled as a point, but it might make sense to model atoms as like different atom types differently, like they have different atomic weights, and we could use those atomic weights and then do weighted Poissons and weighted persistent homology. And these concepts already exist, so it shouldn't be too hard to generalize these results to weighted point sets. And then the third thing for the further future is to think about, like we defined now the distance between crystals using the bottleneck distance, but there are also other ways to define distances between crystals. And then the question is whether our fingerprints are also continuous with respect to those different distances. So yeah, there are many new things to explore. But this is the end of my talk. Thank you for your attention. Do you have any questions?
Wonderful. Thank you so much, Teresa. Before we get to questions, let's all briefly unmute ourselves and applaud for Teresa. So the first question is going to be from Vadim. He chatted it during the talk, but he's going to unmute himself and ask it now. So Vadim, please go ahead.
It's so annoying. I was so tired.
You still seem muted. Maybe not with Zoom, but maybe the hardware.
Oh yeah. Here, I'll ask your question.
Maybe it's better like that.
Oh, there you go. Yep, perfect.
Okay. So thanks for the talk. I was wondering, are there also counterexamples to the former definition, so the wrong one, if one chooses minimal representation with respect to the number of points? Because the counterexamples you gave, they were increasing in the number of points. So, for instance, the twin.
Okay, I see. Yeah. So this is a bit more complicated because we want a fingerprint that is not only invariant, so two different representations should give the same. Two different representations of the same crystal should give the same answer, but also continuous. So two very similar crystals should give very similar answers. And so, of course, you're right that in my counterexamples, I didn't choose the, let's go to one of the counterexamples. I didn't choose the minimal possible example. So here, for example, the second and third unit cell are not as minimal as possible. But imagine I just take one of the points and, oops, sorry, I need to point with the mouse, one of the points, and I slightly move it some direction, then suddenly this periodic point set can't be described with a smaller unit cell, and then I'm forced to take this unit cell. And then I can basically take the same counterexample Just that now it would be a violation not against invariance, but it would be a violation against continuity. Yeah, that's a very good question. That's an important one. Yeah.
Yeah, that's nice. George, please go ahead.
Hi, thank you so much. Very nice talk. Let me put my hand down. This is just, I'm just trying, I'm glad you have that slide up because that's what I'm trying to understand better. Is my intuition right that this basically the phenomenon that you get with these fluctuating persistent indices is because these are torus knots and the closing condition on the knot gives you multiple cycles depending on how it closes. And so that's underlying this counterexample. And sort of connecting to that, the polynomial you're studying, is there a connection to, you know, Jones polynomials or other classifications of knots that relate to this?
It doesn't seem to me so related because somehow we get a polynomial even for things that don't knot at all. Like, I mean, somehow if for example, it's just a cycle or something like this, then okay, good. You also get a Jones polynomial for a trivial knot. But somehow what I want to say is we get different polynomials for cycles that are all trivial knots. So the Jones polynomial should be the same whenever it's a trivial knot. Oh,
I understand. Yeah, I understand. But because, okay, yeah.
Yeah, so the easiest example.
It's just the way persistence works because you pick up cycles in other directions. You don't just pick up the knot. You pick up things, say, quote unquote, orthogonal to it because some two windings set close, and so you have cycles locally. Okay.
Yeah, and
thank you.
I think the easiest example is if you take a cycle that is somehow between two unit cells, so on the boundary between them, and then it appears only j-1 cube times instead of j cube times, because at the boundary you have half a circle here and half a circle, half a circle here, half a circle there, and so they don't count, and therefore you have j-1 cubed instead of j cubed. So yeah.
Interesting. Yeah. So yeah. It seems to me there might be some underlying connection very deep down to the polynomials in knot theory, but I understand why it's not direct, right? It's
but it would be super cool. Yeah.
Yeah. All right. Thanks so much. Very interesting. Thank you.
You're welcome. Thanks.
More questions. All right, Teresa, I have a question. So you mentioned this polynomial fact. And you brought this up related to computability. So you don't need to compute, the limit out forever. Can you say a little bit more about how the polynomial is related to computability? So you only need to go so far until you can recognize this polynomial. Do you know how far you need to go? Things like that?
Yeah. So that's also what we're currently thinking about. Like, this is the reason why it's not so easy to just write down the definition and that's it, because it seems pretty clear that at some point it will start being a polynomial, but which point is this? And we can give some very high upper bounds, but that would in practice probably not be very useful if you know, oh, you only need to compute the, 1000 times 1000 times 1000 copy. And then from that point on, you only need to compute j equals 1000, j equals 1001, 1002, 1003. That's
up
4
to the
different
degree.
values. And then you can fit the polynomial through those 4 values.
That's very nice that you have an upper bound, even if it's too large of an upper bound. That is quite nice.
Yeah, but exactly, it's good to have at least an upper bound. And we are currently thinking if maybe one could even, for a specific periodic point set, compute beforehand at which value it will start becoming polynomial, and then we could use that number to compute the to fit the polynomial through those values. Yeah.
I'll be impolite and sneak in another quick question. So one of your future directions was continuity with respect to other notions of distances, not the bottleneck distances between the underlying points, but other ones. So is is Hausdorff distance something like this? Is this something with which you might expect continuity or?
No, Hausdorff distance, I don't expect continuity, and I kind of don't want to expect continuity, namely in a sense that first, physically, if in Hausdorff distance, you can have 2 points in one periodic point set and 1 point in the other periodic point set, and they would still be happily matched. But in physics, like, what would this mean? That an atom appears out of nowhere close to another atom? That doesn't really make too much sense. And then also it would completely mess up all of our fingerprints, because we always compare one k-fold persistence, like order k persistence, with another order k persistence of the same k. And if you suddenly have more points, then this means that the order k persistence will look somewhat similar to the order k plus 1 persistence in the other set. But if you compare order k with order k, then these would not match well. So
that makes sense.
Yeah, but this is a distance that I came up with that I think seems reasonable to consider when wanting to compare two crystals. And it looks super complicated, but the idea is just that we want to define it such that the crystals are similar if one could just be a measurement error of the other crystal. And so now we already have with the bottleneck distance that the coordinates of the points in the motif, they could just be measurement errors. But what if the vectors measuring the unit cell, what if there's a measurement error in there? That would then completely change the point set, because this error would accumulate the more copies of your unit cell you have. And this definition also allows a slight scaling of the vectors that define the unit cell, but it punishes for, like, the more you scale, the bigger the distance will be, or the more you have to move your points, the bigger the distance will be. So this is basically the punishment for the scaling, and this is just the bottleneck distance as we had it before. So that would be one idea that would be maybe interesting to prove continuity with respect to that distance.
Mm-hmm. Yep, quite practical. Any last questions from anybody? Well, if not, thanks again, Teresa, for a fantastic talk.
Thank you.
See you, everybody. Hope to see you next week. I suppose next week we'll be doing an interview. So Martin Rossen will be interviewing Lisbeth Vetstrup. So, bye-bye.